Poppin' YouTube, Code Adventurers, welcome back to the Advent of Code 2023. Chris here, and last night we embarked on a lens-focused adventure, organizing them into buckets and calculating the total focal length with precision. We navigated the optics with ease, and now with festive spirits in the air, we're stepping into day 16. I hope your code stockings are hung by the chimney with care, and your coding tree is twinkling with festive lights, because tonight's challenge promises to be a coding celebration. If you haven't joined the Code Adventurer crew yet, hit that subscribe button, give it a festive like if you're ready to unwrap the coding joy of day 16, and ring that bell to stay in the loop of all things Advent of Code. After fine-tuning our lens configurations and focusing power, I'm thrilled to see what festive coding surprises day 16 has in store for us. So grab your coding cocoa, clear your coding chimney. Let's code our way through the jolly landscape for day 16 of Advent of Code 2023. Code Adventurers, are you ready to unwrap the joy of another festive coding challenge? Let's code our way into the holiday spirit and conquer another coding victory in 42 seconds. If you're interested, comment below and I can show or demonstrate how I generate these intros. Day 16. The floor will be lava. With a beam of light completely focused somewhere, the reindeer leads you deeper still into the lava production facility. At some point, you realize the steel facility walls have been replaced with cave, and the doorways are just cave, and the floor is cave, and you're pretty sure this is actually just a giant cave. Finally, as you approach what must be the heart of the mountain, you see a bright light in a cavern up ahead. There you discover that the beam of light you so carefully focused is emerging from the cavern wall closest to the facility and pouring all of its energy into a contraption on the opposite side. Upon close inspection, the contraption appears to be a flat, two-dimensional square grid containing empty spaces, which are the periods and mirrors, and splitters. The contraption is aligned so that most of the beam bounces around the grid, but each tile in the grid converts some of the beam's light into heat to melt the rock in the cavern. You note the layout of the contraption, your puzzle input, for example. The beam enters in the top left corner from the left and heading to the right. Then its behavior depends on what it encounters as it moves. If the beam encounters an empty space, it continues in the same direction. If the beam encounters a mirror, the beam is reflected 90 degrees depending on the angle of the mirror. For instance, a rightward moving beam that encounters would continue upward in the mirror's column, while a rightward moving beam that encounters a mirror would continue downward from the mirror's column. If the beam encounters the pointy end of a splitter, the beam passes through the splitter as if the splitter were empty space. Okay? For instance, a rightward moving beam that encounters a splitter would continue in the same direction. Okay, so it's moving left to right. If the beam encounters the flat side of a splitter, the beam is split into two beams, going each of the two direction splitter's pointy ends are pointing. For instance, a rightward moving beam that encounters a pipe splitting would split into two beams, one that continues upwards from the splitter's column and one that continues downward from the splitter's column. Beams do not interact with other beams. A tile can have many beams passing through it at the same time. A tile is energized if that tile has at least one beam passing through it, reflect in it, or split in it. In the above example, here is how the beam of light bounces around the contraption. It's interesting. So I think we enter from the left, we hit the pipe, we go down, we hit this one, which is another splitter, we go left and right. So we go right, we dead end on the left, I guess. We go right, we get suppose a 90, and then a 90, and then a 90, and then a split, and another split. I think because it comes here, yeah, from here it comes here, goes down and up, which is then reflected, which then brings the beam up here, which then hits this splitter, which goes right, which then gives us this down split here. Okay, which would keep going down. And then this one comes up, which comes here, which goes back to the beginning and continues the loop. Okay, so we're going to have a loop scenario. Beams are only shown on empty tiles, arrows indicating the direction of the beams. If a tile contains beams moving in multiple directions, the number of distinct directions is shown instead. Here's the same diagram, but instead only showing whether a tile is energized or not. Okay. Ultimately, in this example, 46 tiles become energized. The light isn't energized enough. Ultimately, in this example, 46 tiles become energized. The light isn't energized enough tiles to produce lava. The light isn't energizing enough tiles to produce lava. To debug the contraption, you need to start by analyzing the current situation with the beam starting in the top left, heading right. How many tiles end up being energized? Okay, so I know that there's going to be a loop. We already see that in this first example here. And I know we're going to have to take that into consideration. Following the beam, fine. We can do that, and then we can split. So we don't care if it's been energized more than once, just whether or not it's energized like this. And I actually kind of like this strategy a little bit. The only thing I'm not a huge fan of is I was thinking in my mind that we would switch the periods or the dots in place to like a value to indicate that it's energized. But the problem that we run into is that the mirrors themselves and the splitters also become energized. So I think it would be better to track that either in a separate grid, so we can create like a parity grid with like all bulls or something the same size, and then we would just, as we would come across the index and we would energize it, we would mark it. Okay, let's take a look at this. So we take this input and we'll open up our freeform. Let's look at this together. So we know the beam is going to start here and it's going to come here. And we won't do the whole thing here, but this splitter here, when we enter from this direction, means that the light is going to go down this way and it's going to go up this way, although that's the end. So it's going to come all the way down. It's going to split two ways, and we'll have to figure out what we're going to do there. I suppose we could just call a recursive function of some sort, but it's going to come. And here's our first point of repetition, is this one right here. So we somehow need to track for this particular one, has it already split? Because we don't want to keep following this beam around. And then we can follow this side, which is something like this. And then like this, like this, like this, like this. And then again, we're back in that same loop. We can do this several different ways. We can maintain just a map as an example. We can call it split, and we can record the XY, and then we can set it to true. I mean, that should be sufficient enough. And then each time we get to a splitter, we'll check to see if it exists in that map. And if it does, we won't proceed. I think that's the way that we handle that. And then we have to figure out how we're going to map each of these things energized. I honestly think we can just use the same map, and maybe we'll call it energized instead. And XY is what we track. And then if split, we'll just set the value to true. And what we'll do is that if the key exists, so if key, then we know that that's our energized point. And the reason we want to do this is because if we enter into something the first time, we want to split. But if we somehow, like in this scenario down here, when we came to that split a second time, we don't want to follow the path again, because we'll just end up with a recursive loop like we have here. We don't want that. So that's why we're going to take that approach. And so I think we just use a map of energized, and then we just have to create an algorithm to follow. And then I think what we'll do is each time we split, we're going to recursively call our algorithm. So we'll say, on split, we call our function with 2 new start points. I think that'll be our strategy. So our function will just take in some sort of start index, or like an XY start. And I think that'll make sense because then we can recursively call, and we won't worry so much about concurrency here because we're not going to concurrently call them, but it should allow us to fork the different directions and walk through the left side and then the right side, and we'll have to indicate some sort of direction. So I think it's going to be like some sort of func x y int, and then like a dir, and this would be, the direction would be up, down, left, or right. That's going to indicate what direction we're heading. So initially, our seed for that func would be 0, 0, right, which would tell us that we need to plus our column to go to the right. And then a down would be a plus of the x, which is our row, and so on and so forth. Then we'll come up with a control for that. So I think that's the plan. So let's look at actually implementing that. We'll just go ahead and grab this test input, and we will put that. So let's look at what is our score. How many tiles? So 46 energized in this example. All right, we run that. Of course, that is not going to return what we want, which is fine. Let's do this then. We know we have a grid, and so we have a helper function for that, which is great. Common dot as grid, and we're going to pull in s and right, and then we're going to all right. Yes, okay. Perfect. So now I can just run the test over here, and I don't need to worry about whatever else is going on. That's what I want. Okay. What is this test? Okay, that's what we wanted. So I'm good with that. So we can focus on the command now, and we can get rid of this. Yeah, perfect. Hopefully this is a little bit better of a view, but let's focus on this. Okay, so now we've got this in this entry, and so what do we want to call this? We want to call, we'll call it beam, whatever. X, Y, int, and then direction, which will be string. And we're going to give it a map, which is a map of string to bool. Okay, that map's going to get passed around a little bit. We'll call fire because beam, whatever. And so in the case of what we have here, it's going to be All right, so we've got our grid. And we are going to fire a beam into G at 0, 0, and the direction is right. And we're going to give it a new map of string to bool that's empty. Okay, so we're going to the right, and we're going to energize I hate the way this looks. Just to be honest with you. Because we're implying that energized false means it's not energized, but what we're saying is actually if it's in here, it's energized. And the bool is an indicator of did we split? So it's kind of serving two purposes. But I'm going with it. It's a terrible name. I could call it split. Maybe it's a better way to do it. Split. Immediately we're gonna do that. So the first thing we need to do is see, okay, is there anything to do at this location? We're moving to this location. Switch on the direction case. All right, we'll go with that. And then so if we're going to the right, there's a couple things that we need to be cognitive of. So we always set the split to false. And so if it's right or left, and if G sub X sub Y equal to a pipe, then our direction is going to split. I guess I could do the bends too, but okay, so we know we're going to beam up and we're going to beam down, right? I guess we can just do some disclaimers. If X is less than 0 or X is greater than or equal to length of G minus 1, or Y is less than 0, or Y is greater than or equal to length of G sub 0 minus 1. We're just going to return because there's nothing for us to do. We're outside of our bounds. Okay. And then, so if this is true, we're going to beam the two directions, and we're going to, there's really, this one comes to an end. So we're going to beam up and we're going to beam down. So if we're coming from the right or from the left and we hit a pipe, we're going to beam. So let's beam up. Let's beam up. So it's going to be G X minus 1, Y, and then we're going up, right? And then split gets passed in. Let's beam down. I mean, I feel like we could just do this for the entire thing and just take this strategy of recursively calling this beam function. So this is going to beam all the way through, and then this is going to beam all the way through. So let's do one more thing here. We're going to say if, just return. So if we hit a condition where we've split previously, we're going to just return true on this particular XY, so we don't reprocess it. Otherwise, we said split equals false. I'm trying to think if there's a way we can get into that problem with the 90s. I don't think so. This is X plus 1. to go down. Okay, I'm debating on this here because this is the same here. We'll think about that in a second. That's the same there. And then for up and down, if we're going up or down and we've got this pipe, then it's the same, but it's the opposite, meaning that we're either going left and right. So this would be left because we're going minus, and this would be right. Okay. And then same thing here. This is also true. So that takes care of our splitting. I know we're splitting here, and I feel like it would be easier to just go ahead and say, hey, we've split. But the problem is that if I have this here, it is going to, I think I could simplify this, but I think the way we're going to do this is by, so if I pass in true here, right, as an example, I think this is what we're going to do. It's a little messy, but I think this is the right way to do it. If we pass that in here, then I can define split bool, and that's always going to be false in the beginning because there was no split when we called 0, 0, right? That might cause us to go through, like if we split right away, I don't know if that is the condition. I'm just going to call this M because I don't like energized either. You know what I could do, make me feel better, is I can create a type called split, which is really just a mapping of bool, and then it would all make logical sense. But I'm not going to. Right. So then this just becomes split. So, but we only want, yeah. Oof. Okay, this is still challenging because if we read off of the map what the value is, meaning we set it, then we run into this problem of if we skip out early. So in other words, if we're crossing across, if we're not splitting, we don't want to necessarily skip that step. So only if it's in here as a split and we're saying split. Yeah, and then one last thing is that we want to check, this is getting messy. Only if it's not set do we want to set it. And the reason for that is because if we're traveling through the pipe, like from left to right, like this pipe over here, if we're coming from top or bottom, we need to split it, and we want to split it, but only if we haven't split it previously. But if we're coming back through here and we're just using it as a pass through, we want to make sure that we're not splitting because of the direction we're heading. But we don't want to set it back to false. So we only want to set it if it's not in the map and it's not true. Do we then set it? So this will prevent us from, in the future, if we come through here and it's found and it's already set to true, we won't set it back to false. So only if it's not okay or it's not true do we go ahead and set it. So if we don't find it, awesome. If it's not true, go ahead and set it. And then I think we'll be okay. All right, so let's focus on this then. So we can shoot these beams in different directions. I honestly think this might be the route we want to take for all of these. So let's think about it from the right direction. If we're going to the right and we hit one of these, Yeah, let's do this. Right. So if we're here, we could just fire the beam at that point. So we don't really need to sort of just end the function and recursively call beam, right? We're firing it in a different direction, not a problem. So if we're coming from the right and we hit this, we're going to go down. So the answer is down, right? And then we return. The other option is right, and if we hit this, then we're going up, and our new direction is up. This becomes false, and this becomes false, because I don't think we have to worry about those reflection points. It's just these splits that are going to get us into a recursive loop. I suppose we could end up in a situation, maybe depending on where we started, where we split down. But no, because we're going to split down at that point. So I don't think we'll ever get into a situation where we're a complete like recursive loop unless the top left corner starts with something, and we can, let's check that real quick. So let's look at our input. So our top left, oh, it absolutely is a down. Okay, see, it's not in the test input, but that's interesting. So it is a down. So theoretically, if we come back here, no, that would put us out. I don't think we can get into this like recursive loop situation with these 90s, so I'm not going to consider that. Maybe we run into that at something in the future. Okay, so we've got those scenarios accounted for, and then so if otherwise, if our direction remains the same, so there's no change in direction, we can just keep iterating forward, right? So if it's a dot or if it's a dash, in the case of the right to left, we don't really care. So I'm going to say that if we're going to the right, then we are moving the y. Y is plus equal 1. And so this is going to be our for loop. Yeah. So as long as direction doesn't change. Okay. So same thing with this. Let's go ahead and handle our left condition. So y plus equal 1 minus equal 1 is going to bring us to the left. And if we're coming from the left and we hit this one, will be minus 1, and this one will be plus 1. I suppose we could do something with the operators here, and if it's left or right, I think this will be fine for now. We can get fancy later if we want to. Okay, so then we've got the up and down. So if we're going up, x minus equal 1, and then if we're on our way up and we hit this, we're going to go, oh, I'm sorry, I almost messed up here. This is up and this is down. Okay. If we're going up and we hit this, we're going to go left, which will be y minus 1, and this will be y plus 1, and we're going to be going right. That's our direction. And then finally, I could have done another switch statement inside of here. That probably would have made a little more sense. We're going down, so our x is moving down. And if we're on our way down and we hit this, we're going to go left. So it'll be minus 1. This one's going to be right. That's going to be plus 1. Okay, so that should be it. So we're going to continually loop as long as we're heading in the same direction in which we set out to head. If we hit any of these conditions where we need to switch the beam direction, then we just send the beam in that other direction and we go from there. On insert into here, because I did see that initial, we said we're going right and we're starting at 0, 0, then I do believe this is going to be accurate. So then after all of that, we beam it, and this is going to be called M. And then we just need the length of M. That should be it. Index 10 with length 10. Aha. So if we go back to our drawing, I suspect this is our issue here. So this is one scenario. The other scenario could be this one here. And so we did not account for that here at each iteration. So we can just simply do that. So yeah, so let me remove that. Let me put it at the bottom of this for loop. So the idea is that as we're moving, we could get into a situation where we're off map. Okay. Actual 18. Got it. Okay, so let's look at zero, 0. I don't see 0, 1 in here. Ah. Aha. Okay. So the reason we don't see 0, 1, but we do see 1, 1 is because I am iterating inside this for loop, and this for loop, it's not marking it in here. So that's a problem. We can move this into our for loop. I think that'll solve my problem. 46, 38. Okay, we're getting somewhere. So 0, 0, 0, 1, expected 46, actual 38, okay. 0, 0, 0, 1, 0, 2 is a thing. 0, 3 was a thing. 0, 4, 0, 5 certainly was a thing. 1, 1, 1, 5. Let's see here. If we're going left, that's going up, that's going down. If we're going up, it's going left. If we're going up, it's going right. Going down, it's going right, it's going left. All right, so we're close. I just got to figure out which ones aren't working correctly here. Let's look at our diagram real quick and see. So let's go with, all of that is good. 0, 1, 2, 0, 1, 2, 3, 4, 5. 2, 5, 6, 7, 8, 9. 2, 5, 6, 7, 8. Why is 2 of 9 not? set. Am I seeing that correctly? 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay, it looks like we're missing 2 of 9. So why would we be missing 2 of 9? 2 of 9 is just an empty. Is this qualifier wrong? Yes. Yes. There we go. That's the issue. Okay, 46 and 40. If x is less than 0, or x is greater than length of g minus 1, or y is less than 0. Y. Is there another place this qualifier is? Yes, it's up here. Okay, that, and go. Okay. We've got 2 of 9 now. Let's check our other edges. So let's 0, 1, 2, 3, 4, 5, 6, 7, 7, 0. 7, 0. Okay. 8, 9, and 1. 9 and 1. I don't see 9 and 1. 9 and 5, but not 9 and 1. I don't see 9 and 4 either. Okay. So, okay, what about, I'm sorry, 9 and 1 and 8 and 1. Sorry. 8 and 1, 8 and 1, 8 and 1, 8 and 1. I don't see 8 and 1 either. Okay. So 8 and 2, 3, 4, 5, 6. 8 and 2, 3, 4, 5, and 6. I've got 8 and 5. 0, 1, 2, 3, 4, 5, 6. 8 and 6, 8 and 7. 0, 1, 2, 3, 4, 5, 6, and 7. Okay. Why is 8 and 5 true? Ah, okay. So one last mistake. If the first time through, because we're going to a split, it should set split. But if we're continuing in that direction, it shouldn't. Okay, there we go. All right, so we need to provide the puzzle input. And so we're going to put that here. And 7953. All right, I just realized my second mistake. Let's go to draw. Let's just look at it. I mean, we know I'm not going to do this in rocket time, so let's we'll scroll down here for a second. Come down here. So let's presume I have a scenario where I've got a pipe and I don't know from what direction, but let's say a beam is coming this direction. And it splits That's okay. Actually, if it comes from the other direction, it's still going to split the same. So I think that's fine. Upon closer inspection, the contraption appears to be flat, two-dimensional square grids containing empty space, mirrors, and the beam encounters empty space, continues in the same direction. Beams do not interact with other beams. The tile can have many beams passing through it at the same time. A tile is energized if that tile has at least one beam passing through it. Reflect in it or split in it. Okay, those numbers are correct. Is the initial direction right? I don't know if that's throwing me off or what. Upon closer inspection, the contraption appears to be a flat mirror. The beam enters in the top left corner from the left and heading to the right. So it's moving right. Okay. So let's clarify that. Right. And it's got nothing in there. Got it. Okay. The beam encounters a mirror. If we encounter this from the right, we are going to do x plus 1, which will give us a downward momentum, and our direction will be down. So let's look at this. So let's just say 0, 1, 0, 2, 3, 4, 5. So like we should get a bunch of zeros in our output, right? So 0, 0, 0, 100, 0, 101, 108, 109, 14, 19, 21, 20, 0, 30, 38. I don't see 0, 1. Yeah, okay. So we know what the problem is. So we'll presume it enters here and it's going to come in. It shouldn't find this. It's going to take the XY. It should find that it's not okay. Right? Because that's what should happen. As we come in and we're going to bounce. Let's just make sure. Okay. So we're moving down. That's great. X plus 1 down. Oh, I'm sorry. Okay, so it's not 0, 1. It's 1, 0. Okay. Let's rerun this. Oh, I didn't notice this was wrapping either. That's interesting. Okay. Well, let's switch our view then to here. But let me think through this. So we're going to the right. We're going up. We're going down. That's right. If we're going from the right and we hit one of these, we're going down. So it's x plus 1. If we hit one of these, we're going up. It's x minus 1. Left. Both of these. Okay, good. If it's this from the left, so we're going this way, we're going to go up x minus 1. We're going to go down x plus 1. Okay. And to the right is plus y. To the left is minus y. All right, up. If we're going up, we hit one of these. We want to go left. Sorry, we're going to go right, which is plus, left, which is minus. Yeah. Wow, that's interesting. Maybe I lucked out, but in the test example. But what's going on here is that I'm setting the next index as split and not the current one. So that's really the challenge here, is that the current one needs to be marked split, not the next one. So what I'm going to do instead is we'll go ahead and mark the current one split here. I think this is just going to simplify our logic, because we're not going to the one we're splitting and changing directions. We're going to the next one in the iteration. And so that takes care of that. I think we can actually remove the split bool entirely. And if this is true, then yes. And then this also is still kind of true. And that is if, yeah, because again, we don't care here. We should pass by it because we don't really care either. So we really only care here is that we want to catalog it. So this becomes unimportant. And if not okay, then false. Right. Okay. So we don't care about the split as much anymore. And I think this is true because we're going to catalog it where we should have been cataloging it the whole time, which is at the point of split. So let's talk about how this should work in theory real quick and the errors of my ways. So I think all this is fine. If we're coming from up and down, we pass a pipe, we're not even going to split our beam at all. So we're just going to keep processing forward. So we're not even really check this condition. Only if we split our beam, this check here needs to also be here and here and here. I think this code could probably be cleaned up a little bit, but at this point, I'm just trying to make it work. Okay. And actually, this check can be removed now. Okay, test still pass. And what do we get here? 7953, 8112. That's it. All right, awesome. Error of my ways. Moving on to part 2. Part 2, as you try to work out what might be wrong, the reindeer tugs on your shirt and leads you to a nearby control panel. There, a collection of buttons lets you align the contraption so that the beam enters from any edge tile, and heading away from the edge, you can choose either of 2 directions for the beam. If it starts on a corner, for instance, if the beam starts in the bottom right corner, it can start heading either left or upward. So the beam could start on any tile in the top row heading downward, any tile in the bottom row heading upward, any tile in the leftmost column heading right, or any tile in the rightmost column heading left. To produce lava, you need to find the configuration that energizes as many tiles as possible. The above example, this can be achieved by starting the beam in the 4th tile from the left in the top row. Using the configuration, 51 tiles are energized. Find the initial beam configuration that energizes the largest number of tiles. How many tiles are energized in that configuration? So we've got 110, was it? 110 inputs by 110. So that's like what, 220, 440 checks. It's not too bad. So for part 2, let's implement part 2. So really we just need to do the same thing, but our entry point changes. So part 2, and then we just got to keep the high score. So bar score int 0, and we just need to return that. So we'll go ahead and get rid of some of these prints now. We'll get rid of these 2 and this one here. So what we're going to do is we're going to say for, because we're not actually manipulating the main grid, we're mapping, right? So we can pull this map in for each one. And then we can say for the range of grid so if this is all the x's, we can do it like this. And so that's going to start everything at starting on the left hand side. And then we can just say, yeah, so that's pretty straightforward. We just need to do this 4 times, right? So we just need to iterate between the x and the y. There's probably a more elegant way to do this, but I'm just going to copy it for each one. And so we'll talk about a more elegant solution here in a second. Right side, down or up, and then down, right? Okay, so everything's starting from the left. So x of 0, and then x of length of g sub 0 minus 1, and we're going left. And then really should be g sub 0, even though the grid's the same size. We'll call this y, and this will be 0 and y. And so this will be the top row at the different columns. So this is going to be going down. And then again here with the y, this is going to be length of g minus 1 and then y. So it'll be the bottom row, and we'll just, again, with the 0. And so that will loop through each one, and only when the score is greater, and then we'll do score here. Maybe we'll talk about a more elegant solution here in a second, but let's go with part 2. Let's test part 2. That was pretty fast. Let's test part 2. I guess I could just run with it, but we're here, right? 51. 51. Okay, cool. So that did test out. Oops. Let's just try it. 2 numbers. 2 number difference. There we go. Awesome. part 2 complete. All right, let's optimize a little bit. Part 1 had me for a little bit of a tiz, and I'm not a huge fan of that. Is there a way that I can make this? Oh, whoops. Does that change the answer? Well, that's interesting. I got lucky there. Let's kind of walk through what we did here, and we'll kind of explain the problem. I think it'd be good to review the problem and then the solution. So first, what's our problem? Day 16, the floor is going to be lava. So we have to basically create lava with beams of light, not focusing, figuring out how many things are energized with the mirror configuration, and then figure out what the optimal or the entry point, depending on if it enters from top, left, right, which one produces the most amount of energized squares. An energized square is considered if the beam passes through it. So that's pretty much that. So the way that we're going to do this is each pipe, dots are just empty spaces, but each character, so there's a dash, a pipe, and then these two forward backslashes, they each indicate something depending on the direction you're coming from. And so as you can see here in this diagram, if we run from, like, let's say left to right, and we hit this kind of pipe, we split it going up and down. And then if we going up and down and we hit this dash, you split it going left and right. So we want to know how many of those are energized. Here's kind of a representation of what's been energized. So there's a couple different ways we could do that, but I chose to track that in a map just because I find that the keys are easier to handle, and then we could add more data structures with it. Alternatively, we could have just like pre-populated some sort of like slice or with empties, and then maybe turn them on as we process them, or we could use some sort of struct. That's also possible, but a map worked just fine. The benefit with the map is that you do get pretty fast lookups, although XY index lookups are pretty fast, but I could also do more with it, and I'm only going to fill up what's actually used. The downside is I was using strings as keys, so there's some data footprint from that. So let's talk about part 1. So the implementation in part 1 was pretty straightforward. We took a grid and we would create a beam across that grid. And the rule for part 1 is that you always started at 0, 0 and you were headed in the direction right. And then there was a map that was created to track these things. So if we'll skip past part 2 for a second, if we look at our beam function, we just had some gating exits. So if we exceeded off the map, we would just return and we wouldn't do anything. If that wasn't true, then we would go through this for loop, and we wanted to check our map because we're using our map for 2 purposes. One was to check how many cells were energized or how many XY positions were energized. And then the second part was if we ran into a situation, if we go back to this example here, if we ran into a situation like this, right here would be a great example. We would have gotten to an endless loop if we resplit this every time. If you look at the red track, we're constantly going back to this beginning position. So we wanted to mark that we split that previously so that once we split it once, we knew we didn't have to split it again. So that's what that implementation was for. But if it's not set, then we're going to set it false. This can be removed. This was just for debugging and troubleshooting. I ran into some issues. Let's talk about the directions. So then based on the direction, I chose to just use a recursive function. So refiring the beam instead of changing XYs. I thought it would be easier to think about in this way. So I decided to just repoint the beam using a recursive function. Since we're not actually modifying the grid, we could just pass it around. And since the map is essentially acts as a pointer inside Go, we can pass that around and modify it in multiple functions. In theory, we could do this concurrently, but we would just need a concurrent map instead of a regular map, just so we don't run into read-write concurrency, but it wasn't necessary for this problem. So really, we just go through a set of steps. I won't bore you with all the details, but if we're headed right, we look for a couple of conditions, and depending on those conditions, we redirect the beam. If we don't meet those three conditions, then we just keep moving forward with the Y in that direction. Same thing with left, up, and down. And then I just have a default in here to panic that we messed up. If ultimately we loop through and again we find ourselves outside the boundary, we return. And so this will allow us to call beam as many times as necessary to get through and change your direction, and it kind of simplifies our function. So part 2 is just a continuation on part 1. The difference here is that we had to figure out which one was the optimal entry point. In part 1, we were entering just from the top north. In part 2, we had to try all the top, left, right, and bottom entries. And depending on which side we enter from, you're headed in the opposite direction. I suppose the one thing that I did leave out is that if you start in the corners, you could head either left or upward. I didn't really implement that, I did implement that. I'm sorry. So that was one additional thing there. And then as you can see here, our test input was 51. So the way I handled that for part 2 was just simply iterating through and incrementing the row in the 0th position, and then we would grab the score each time. The right side, the same thing, up and down. I actually messed up on the down because it was moving right, but apparently my direction was above, and then simply getting the score of energized. And in my case, I think it only changed by, we can actually look, changed by 302 or 202 was the difference in the score. So that's pretty much it for the approach. The mistake I made was getting hung up on, in part 1, in the beams, I was projecting the split into the future as opposed to setting it in each one. That's all I have for today. As always, I hope you liked the content. If you learned something, please like and subscribe. I'll see you next time. Over and out.